It's a change in pitch, either due to what? Relative motion. That's called the Doppler effect. Relative motion between the source and the receiver. Oh, C. Come on. That's a C. Looks like an S there. Why they call it the Doppler effect? It was named after Christian Doppler, actually, some French physicist. That's where the name came, Doppler. Notice it says the change in pitch due to relative motion. It could be the source is moving, it could be the receiver is moving, it could be both are moving. We're going to look at the three cases. Moving receiver, that's the first one. So we're going to look at the moving, the person. So the observer is moving. The receiver, the one listening to the sound, is moving. An example here, you have a boombox playing here, music. That's supposed to be a boombox. And the music is coming out of it. And you're listening to music. But instead of you actually listening to it here, walking, maybe you're riding a bicycle. That's you on the bike. And it could be two things. You could be going this way, you could be going that way. So notice you, the receiver, actually moving toward the box. The source is not moving, but the receiver is moving. And the question, if the signal coming out of this for the certain frequency, like the beat, let's say somebody's sitting there playing a drum, bum, 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 there's a frequency to that. The frequency for this, we'll call it F. How fast this one's going to hear them, we'll call it F prime. The frequency. Is that frequency going to be faster or slower than F? Well, it depends if you're going toward the source or you're going away from the source. Now we're going to give the observer a speed of u. That's the speed of the person here. The source is going to have a speed in air here, v, which is what? 343 meters per second. Remember that? Well, here's what we know. I'll derive the equation for you. We know the velocity of the sound going this way. The velocity is equal to what? The equation for that is lambda times f. That's the equation for velocity. This one here, f prime, if you look at that, is the velocity here over lambda. But wait a minute, the velocity, how fast that sound approaching you. Just think about this now. If you're in your car going this way at 10 miles per hour, and there's a car going this way at 50 miles per hour, what is the speed you're going toward each other? This one going 50 and you going 10. Don't you add them? So to you it looks like you're not moving and that car is coming at 60 miles per hour. So the speed for this It's really the speed of this plus how fast are you riding your bike there. That's how fast you're moving. I don't like the word lambda here, so I might replace lambda with this v divided by f. So I end up with f prime equals v plus u. In place of lambda from here, that's v over f. And if you do the math, you end up with what? V plus u over v times f. That's equal to f prime. That's the equation that describes what the frequency is going to be. It really should be plus or minus. It depends if you're going toward it or you're moving away from it. If you're going away from it, this equation becomes, instead of plus, becomes what? Minus. So this is going to it if you go in that direction, but if you're going away from it, in this case, would be v minus u over v times f equals f prime. This is for going away. So a lot of times when you look in a physics book, that equation is written as plus or minus. It will look like this. V plus or minus it depends if you're going toward the source or you're moving away from the source. We'll take an example. Not here in Springfield, but if you go to New York City or go to Boston, you hear these musicians playing music on in the street there. So you have a musician who's playing, I don't know, an instrument here on the street. There's the musician here. He's playing an instrument, and you're actually riding your bike. So you're coming this way on your bike. We'll use bicycle again. That's you. And you're going this way. You get to that musician, then you're going to move away from it. Continue riding your bike. Could be running, actually, or riding your bike. Doesn't really matter. We can give you any story. But you continue to ride your bike, passing by that musician. God. And now you continue to go in that direction. Let me give you some numbers here. The frequency the musician creating here for his music is 440 hertz. If you're on your bike at a velocity equals 11 meters per second and you continue at that rate, what is the frequency here approaching the musician, and what is the frequency here going away from the musician? We'll call it 1 and 2. Remember, you're playing the music, so the music is traveling in both directions like this. And you're going toward that. Here you're going away from it. So for F1, you're approaching that. It's going to be mu plus v, or v plus mu over v times f. 343 is v. Add to it mu, which is 11 over 343 times the frequency, which is 440. .343 plus 11 divided by 343 times 440. The frequency for you is 454 hertz. So the sound is coming at you faster. Again, if you imagine somebody's hitting a drum 440 times per second, If you're on the bike going in, you're going to hear that noise, not 440 times per second, you're going to hear it what? 454 times per second. It's going to be faster, like this. If you're going away from it, it's going to be what? V minus mu over V times F. It's going to be 343 minus the 11 over 343 times the 440. .343 minus the 11 divided by 343 times the 440. You're going to hear actual frequency 425. So if the sound of the drum is like this, you're going to hear it slower because you're going away from it. So you're approaching, it's going to be faster. Once you get to the person, the same sound, then you're slowing down. After you hear it less and less, the frequency will be less. Then the intensity will fade away and you won't hear anything. So notice the source did not move, the receiver did move. The next case, the receiver is not going to move, the source is going to move. That's what the Doppler effect, when one of them moves or both of them move. So it could be either one. In this case, the source did not move, but the receiver did move. Let's look at the other case. What will happen if the source moves, but the receiver doesn't? And again, you're at the stoplight and you hear a siren coming from behind you. The siren, the ambulance is moving and you're not moving. So this is moving source. So here's the siren. The ambulance or police car coming. There's the police car, the siren here. The source is moving. V is moving. There's you. Your velocity is 0. You're not moving. That's you. So the police car has a speed of whatever speed is going. We'll call it u here. Moving source, you are not moving. Moving source, receiver not moving. Again, you hear some sirens coming, and it's coming toward you. And eventually it's going to pass you, and they're going to continue. So as they're approaching you, that speed is coming toward you, then it's going away from you. The same thing. We're going to have two equations, one for going away toward you, one for going away from you. For approaching you, for going toward you, we'll go F prime is going to be V over V minus U times F. And a lot of times they take this equation, rewrite, just divide everything by V, and it will look like this. 1 over 1 minus U over V times F. What happens here? They divided every one of these by V. If you divide by V, that's 1, 1, and that's U over V. It's the same thing. Away from you, is going to be V over V plus U times F, which means 1 over 1 plus U over V times F. Now, why is it minus when it's approaching you? If the siren is approaching you, that frequency should be increasing. So when you have a fraction, what happens to the bottom if it gets smaller? Because that number doesn't change. That's 343. What happens if the bottom gets smaller? the fraction becomes bigger, the frequency becomes larger. When it passes you, now it's passing you, the frequency should slow down. It's going away from you. This number gets bigger, and 1 over a bigger number, or 343 over a bigger number, becomes less. And that's why it's minus here and plus there. So the equation that you'll see in a book, it's V over, or V minus plus. They put minus on the top, plus on the bottom. The first value is always toward you, the second one away from you. Or 1 over 1 minus the plus u over v times f. So the first one is for going toward you, and this one going away from you. We'll do an example on that. You're standing on the side of the road. You are standing here, and you see an 18-wheeler going by you, coming toward you. It's an 18-wheeler. It's moving this way. A speed of, I don't know, 20 meters per second. 45, 46 miles per hour. Honks the horn as he's approaching you. Then continues after that. We'll do it both ways. The truck gets smaller suddenly. Same speed, and still honking the horn. What do you hear? What's the frequency here when it's approaching you? And what's the frequency here when it's going away from you? Approaching you, the frequency will be V over V minus U times F. V is 343. 343 minus 20. And I never gave you the frequency. That horn he was buzzing on. Let's give a number for that. Could be a siren, whatever. Let's say the frequency here, F, is 650 hertz. It's a siren. Boop, boop, boop. Times 650. $343 divided by parentheses 343 minus the 20, and you multiply that by 650. I came up with 690 hertz. So because you're approaching you, the frequency is bigger, larger. When it passes you now, it should be slower. It should be V over V plus U times F. 343 over 343 plus 20 times the 650. Let's see if the frequency is slower. Did you get 614? So as they pass you, that frequency becomes slower, but when they're coming toward you, that frequency, that siren going off there, the speed is increasing. It's faster than the normal speed. In the last case, I'll put the equation and we'll ship you home. I know it's getting late. When both of them are moving, the source is moving and the receiver is moving. And basically take the two equations, put them together. Does even our book talk about that? Yes. When the source is moving and the receiver is moving. So here both are moving. So the source here, siren's going off, has a speed, we'll call it mu s. That's the source. And there's u. driving this way. They're not coming after you. They're going after somebody else. And there's you going that way. You have a speed O for observer. You're the person in the car. Then they're going to pass you and the cruiser continues. And the siren's going off. Now, since you're going toward each other here, it should be much, much faster, the frequency. But as you pass you're going away from each other. That'll be less. So we'll call this F1 prime. We'll call this F2 prime. Well, the equation to use here, F1 prime, or F prime, is equal to, when they're approaching each other like this one, is going to be 1 plus mu observer over V over 1 minus mu source over V times F. By the way, that equation a lot of times is written V plus mu 0, V minus mu S. I like that better. Here, it's going to be the reverse. It's going to be slower. 1 minus mu 0 over V over 1 plus mu S over V times F, which you can write that as V minus mu O over V plus mu S times F. Let's give you some numbers, go through it, and go home. The cruiser is going at 60 miles per hour, 60 divided by 2.25 or 24, whatever. The cruiser is going at speed here of 24 meters per second. You going 40, 40 divided by 2.24, 18 meters per second. Continue to go at the same speed. If you're approaching each other, how fast that, and let's say the frequency here is 500. What's F1 bar is going to be? 343 plus, the observer is moving at what? 18 over 343 minus the source moving at what? 24 times the 500. 343 plus the 18 divided by parentheses 343 minus the 24 times the 500. 565 hertz. Here, as you're going away from each other, is going to be 343 minus the 18 over 343 plus the 24 times the 500.
343 was given?
That's the speed of in air. Speed of sound in air.
Oh,
Times the 500. And we are going to hear that noise at 442.8. 443 is good, hertz. And that's the end of the chapter. That's all we have to know.